Hi, good to have you back. Putting a similarity index into production at scale is a pretty hard challenge. It requires a whole bunch of infrastructure working closely together. You need to handle a large amount of data at low latency. It introduces you to topics like sharding, hashing, trees, load balancing, efficient data transfer, data replication, and much more. Believe me, that is nothing you want to team your work on. Rather, use a well-implemented service like Google Vertex matching engine and save yourself a lot of time. So let us get started. According to Google, Vertex matching engine provides the industry-leading, high-scale, low-latency vector similarity search. And I can agree, at least for the query response times, this is true. Follow me along this video to see how it works. Imagine for a second the programmatic effort needed to implement an algorithm to visually compare t-shirts to find matching ones. Achieving good results with traditional programming approaches is just not feasible. Nowadays, we can use machine learning and vector similarity search to achieve great results. And we can easily scale this to an unlimited number of different use cases. It can be used for various kinds of data like text, audio, video, tabular data, item pairs, and different use cases. Recommendation engines, for example, fraud detection, so there are no limitations on how you can use it. Let us start with the vectors. We need them before we can create our Google Vertex matching engine. Feature vectors, also called embeddings, are usually created using a deep neural network or any other type of algorithm you might have. If you already have machine learning in place at your company, you most likely know how you can create them. Usually, you train your own models, create those embeddings based on your data. Or maybe you use a pre-trained model. I covered implementation later on when we switch to the code, so we go into the details as well. The input for the matching engine itself is simple. In this example, I use a JSON file where each row contains a vector and an ID. The response of the matching engine includes exactly those IDs. ID 0, for example, could be internally mapping to the movie Avengers, for example, and ID 1 could be just a lot of things. Other file formats obviously are also supported, and this is CSV and Afro. The matching engine provides two algorithms we can choose from. Approximate nearest neighbor is used in production environments, and it builds a tree using hashing to find similar vectors in a more efficient way. And the second one is a brute force algorithm, which is basically just doing linear search, obviously less performant, and it's mostly used in development as it has a high latency. There's one exemption: if your number of embeddings is less than 100,000, I recommend using the brute force index because you get similar performance out of it. To reduce the network latency for the vector matching queries, a VPC network is required. You might ask, why we even need a VPC network? And I agree with you, this requirement is just cumbersome. In the Google documentation, you find a quote on the right side here on the slides, which sounds like an optional step, right? Trust me, you need a VPC network, it will not work without it. Anyway, don't worry, it's a one-time setup, so don't worry too much. I just do a TLDR now, we go into all the details later in our demo. The initial step we need to create a network with a regional endpoint and add a few firewall routes for ICMP, RDP, TCP, and SSH, as well as traffic to internal Google services on a specific IP range. And we also need to allocate IPs for our nodes. I recommend to over-allocate to prevent IP exhaustion errors in case you need to scale up the environments. And finally, we need to create this VPC peering connection between our VPC network and the Google VPC network where the matching engine is located. This sounds horrible if you're not familiar with network topics, but don't worry, we go through all the steps, and Google-like, it's very well documented. Before we start with Vertex matching engine, first we have to look on how we can create embeddings. This is just one way of many, but it's one of the easiest ones, so it's good for you to get started. I like to use sentence transformers, a Python library. I already installed it here. I don't install it again. And then we scroll down, and then we import the sentence transformer, and we can use multiple models with the sentence transformer. So in this case, I use the sentence T5 base, so a T5 transformer model, and it's now already loaded. And then we have one or multiple sentences. In this case, I have the sentence, "Do it is a great company to work for," and I want to get the embeddings for it. So I take the model and we encode this sentence, and then we get the embeddings. And if we actually execute this, you see a really large array of values, And to be precise, it's 768 elements long. So this is the vector representation for this text. This is how we can create embeddings. And this is what our matching engine needs to actually build the index. And just for this example, we take a couple of more sentences. The first couple of ones are all related to some medical stuff. Then we have a few which are related to cats. And finally, we have an unrelated one which is related to airplanes. So we take the sentences, and for all of those sentences, we get the embeddings and store them in a JSON format. And if we do this, it takes just a couple of seconds, so it's already done. And if you have a look into the file system, we have a data JSON. And if you remember the slides from previously, the format looks exactly the same. So this is the input format for our matching engine. We have multiple rows. Each row is one sentence. We have an ID, which is the unique identifier for this row and for this embedding. And finally, we have the embedding as a presentation as a vector. And now we can start with Vertex matching engine. So the first thing, I need to authenticate this notebook in order to be able to communicate from within the notebook with Google Cloud. So I do the authentication, you get a pop-up, you have to select your Google account, and that's done. Then you have to install Google Cloud AI Platform because we now want to interact with the Vertex matching engine. I already installed it in this case. And we do some imports for our dependencies for the AI Platform SDK. Then we set some environment variables like the endpoint, project ID, a parent, which is nothing else than the project ID in the region. And I also set the project number, which will be needed later on in the project. And finally, we upload the data to Google Cloud because we need the data to be available in Google Cloud in order to be able to be accessed from the Vertex matching engine. I promised we also go over the details on how you can create the VPC network. So it all starts by creating the actual network. Make sure you give names which are understandable so you know exactly this network is related to the matching engine. And in this case, I create a network with a regional routing. That's how it's defined from the Google side. Nothing special here, so we just create a network. And then we set up a bunch of firewall rules. The first one is for ICMP. You see it here, allow ICMP. The second one is are the Google internal services, which run on a specific IP range. And then we have SSH and RDP on the both TCP ports. So this is how the matching engine communicates, and those need to be available on the network. The next one, we need to define the IP range for our nodes. And I overutilize by defining a bigger prefix, 16, and you can do this as well. And the next one, we have to enable the Google API services because this is how our network later communicates with the service networking API. And finally, we connect our VPC network with the Google's VPC network. You see it here. We're connecting our network to this service network here. Here's our network. Here's the Google service within our peering range name. And that's it. That's the basic setup for the VPC. Your index requires metadata, which is just the configuration parameters of your index and your algorithm. The minimum configuration requires a bucket path containing the embeddings as a CSV or the JSON we just created or AFRO file. Then we need a dimension, the length of our vectors, and the vector length depends on the ML model you're using. Keep in mind, the vector length has to be the same for the complete index. You cannot add a different vector length to the index. Then we have the distance type, so the way we want to measure distance. Google provides L2, L1 distance, as well as cosine and dot product. Which to choose depends on the embeddings and, for example, if they're normalized or not. And if you're not too sure which one to choose the cosinus and also evaluate the dot product. The last mandatory parameter is the approximated nearest neighbor count. It describes how many neighbors are included in the approximated search. Increasing this value can increase latency. This is due to a reordering, which might be required if results from multiple trees needs to be included. This is just a minimum configuration. The full list of parameters is obviously documented. And with that, we go over to the code and we actually create our very first index. To create the index, I'm using the Vertex AI SDK. You could also use the gcloud commands if you want to. The first thing we need to do, I need to create an index client, index service client. So we want to create an index, right? So we need the index service client. And then we have this configuration we just covered. And you exactly see where you have the dimension, 768, so the same embedding length we just created in the previous section. Then we have the conta delta URI. This is exactly where we uploaded our data. We also have the approximated nearest neighbor counts, and we have the algorithm configuration. So we have a approximated nearest neighbor algorithm, and I also define a display name, so I exactly know what kind of index we're actually building here. So we execute this. Now we have our configuration, and we create our index by using the SDK. And now the index is getting created. And this now can take up to 30, 45 minutes, depending on the size of your index. And you can check if it's done or not by polling the operations or by just polling the AAN index response. And you get a done Boolean flag if it's done. So now we have to wait. And I pause the video. For me, it's probably a couple of more minutes than for you, and then we come back. The index is now created. It took approximately 30 minutes, and we can check that again by polling done. And so you see, yes, it's true. We also have a resource name for our index. And if we go to Vertex AI and we open matching engine, we see our index here. And if we click into it, we see our description. So it contains medical and cat content. And we also see when it was created and when it was last updated. So we now have our index, and the next thing we need is our endpoint. Creating the actual endpoint is straightforward. We only need to provide our VPC network, so there's no magic involved here. But keep in mind, the matching engine endpoint is not yet ready to use. We still need to deploy our index to it. So for that, let's head over to the code. And similar, like with the index, we also create an index endpoint service client. Then we define our VPC network name, which is this defined string with this templates too, with two templates. And we define our index endpoint. We just define a display name and define our network. And that's already it. Then we can create the endpoint, and we can have a check. So endpoint is already created. And we go back again to Vertex AI, matching engine, go to index endpoints. And we see the index endpoint for demo. So as you can see, this is exactly the name we choose here as well. And this is for our demo now. So the index endpoint is now created. And finally, we deploy our index to our endpoint. This is a one-time job, and it takes approximately 30 minutes. After the model is deployed to the endpoint, we get an IP, which is then used to query our index endpoint. So do this in the code as well. So we deploy our index. So we now have the index resource name. Now this is something you need to define. And we go here to Vertex AI, just to get a feeling how it's working. We take the ID and we just place it here. So index are defined by ID. And then we define a deployed index ID name, so identifier. So similar text index deployed. Then we define our index object. So we have an index resource name, the deployed index ID, and the deployed index ID as the ID as well. And then we deploy our index. And this, again, as I said, takes a few more minutes. So I pause here again, see you in a couple of seconds. The Vertex AI matching engine index is deployed. And if we go to Vertex AI again, to our index endpoints, we have our index endpoint. And there we now see a deployed index. And if we have a look into it, we can see the gRPC IP address, which we now use to actually query the endpoint. So before we now soon start and query our index, first let's talk about how we can actually update our index. Remember the JSON we created as input for the matching engine? Each row has a unique ID. This ID is used during the update process. You can change existing or add new vectors by uploading additional JSON files to the Google Cloud Storage location. To remove vectors, you need to delete the JSON files containing the IDs. Keep in mind and figure that out what's the best way to handle your data, because every requirements are unique. If you have multiple files with the same ID, matching engine will always use the latest uploaded file to index. And the update, again, approximately takes the same time as the initial index creation. Scaling your environment is not a black box. There are recommendations. And if you combine them with load testing results, you're good to go. Generally, we scale by increasing the number of replicas. Each shard can host approximately 20 GB of data, and each replica per shard can serve up to 1000 queries per second. The service is covered by Google SLAs only if you have at least a minimum of 2 replicas, and sharding is done internally, but we need to know that there's sharding in place in order to be able to calculate the pricing properly and the scaling properly. So let us do the calculation. Assuming we have 30 GB of data and we expect around 1300 queries per second. To host the data, we need 2 shards because we can serve up to 20 GB per shard. And to serve the queries per second, we need also 2 shards because we can serve up to 1000 queries per second and we have 1300, so we need 2 shards. This sums up to 4 replicas. So this is how you can calculate your scaling and you get your pricing. Don't blindly rely on these recommendations. The number of replicas you need to handle your loads depend also on the embedding size of your embeddings. And I recommend to do load testing properly upfront to know what is the proper scaling for your use case. By the way, downscaling to 0 is not possible. I think that probably the reason for that is the too complex infrastructure needed to actually put this at scale. Unfortunately, querying is not as straightforward as you're used to with Google services. A few challenges make it a little bit more complicated than it has to be. This is because our endpoints can be only called from within the VPC network. This is obviously bad if you do development and you always need to spin up a notebook rather than just using your local development environment, and similar complicated if your application that is calling the matching engine is outside of Google Cloud. Additionally, requests are only possible with gRCP. This is fine, but it's additional overhead on top of it. To query the Vertex AI matching engine, we need to be in the same VPC network. And for that, we use a managed Vertex AI workbench notebook. And when we create a notebook, we have the possibility to define the VPC network this notebook is working in. So if you create a notebook and you go to advanced settings, scroll down, you can select network in this project. And there you have your Vertex AI VPC network, which we created previously. So you have to choose this, and then you can create your Vertex AI notebook. I go back because I already created this to save us some time. So I open the Jupyter Colab notebook. The code to execute the query is, as always, in the video description. So feel free to use it if you want to. It takes a couple of seconds till the notebook is loaded. So now we have the notebook loaded, and if we have a look, I just uploaded the same notebook here, so we open it. And then we go to the index, go down to actually querying the Vertex AI matching engine. And we use gRPC for that. gRPC is an open source remote protocol. It's used for high performance communication between services. Doing the queries requires a few steps. The first thing we need to do is we have to use a compiler to compile our proto buffer file into a client code, so our native Python code, for example. Other languages supported as well. And for that, we use a library which is called gRPC IO tools. So we installed it. I did it already, so I scroll down. And then we have to define the protocol buffer for our matching service endpoint. This is how the protocol buffer looks. It's standard, so it's standardized format. So we write our protocol buffer down and write that to a file. So if we go to the file system, you now see we have a Vertex matching service proto file. And now we take this proto file and use our compiler. So we now take our compiler by calling Python gRPC tools protoc for proto compiler, and we define our proto file. Yeah. And now we get two Python files. And if you have a look into it, you see this is actually Python code which we can execute. And this is all what we need in order to execute and run our queries. So we can now go down, and you see here the code needed to actually call the endpoint. So we have our server IP here, and we have our deployed index ID, both we need. And then we have our Python implementation to call the matching service, and a little bit of boilerplate code here. And we create a matching service stub. So we do this. And then we have to put our embeddings, because we are querying our matching service index also with embeddings. I skipped this step, so we quickly go up a little bit. And we create the embeddings in exactly the same way like we did before. We take our model and get our encodings out of it, our embeddings. So I have a sentence, the cat likes to sleep in the sun, and this is our vector embedding out of it. So we take this vector embedding and send it to the Vertex matching endpoint by adding just a float value appending to our request. And then we get a response back. This is now our similarity results. And in this use case, we get ID 7 as the highest similarity. Then we get ID 4, ID 6, and ID 5. And if you have a look into it, I put it here down. So this was our input sentence. And we get 7 as the best result with the highest similarity. And you see it's also related about cats, and even a cat sleeping. So you see we have here cat sleeping and here cat sleeping. So this has the highest similarity. The second highest is with ID number 4. And if we have a look into ID number 4, it's also related to cats. And this goes down till we have all the stuff cats related. So we have 6. 6 is also related to cats. Then we have 5. 5 is also still related to cats. And then we get 8. It's the first one which is not related to cats. And you see the similarity changed from 5 to 8. The similarity changed a bit. So this is the text with a lower similarity. This is how it works. This is how you can access the similarity endpoint and get your response back. If you like this video, make sure to subscribe. The code for this video is in the description below, and I also have a deep dive article. Additionally, I plan to release a new video how you can implement the Cloud Run service endpoint to make your matching engine endpoint more accessible. So see you there. Bye.